in here, we have the evaluative report synthesis, which means that you guys are going to make these chemicals, an analysis, which means that you guys are going to figure out what the formula is of 3 nickel salts. Okay, this is summary of points. This is the procedure, which is basically just the write-up that you would see in the lab manual, but you really want to start in the data and observation. This is where you guys will find the information. The first part is just the PowerPoint of the synthesis and the analysis of the nickel salt. This part right here gives you information of the synthesis part. This part right here gives you the information about the analysis part. This is going to be the data. You want this data because this is what you guys are going to be using when you do the calculations. This is 3 trials of the analysis for salt A. It's 1 salt that weighs 1.2801. That's your initial mass. This is your final mass of the product. Okay, so in the synthesis, you start out with 1.2801 of nickel sulfate hexahydrate. Your finished product is 1.2582. We're doing the 3 trials. I guess this is the average. This is trial 1, 2, and 3 for salt B. This is trial 1, 2, and 3 for salt C. Anyway, I will talk to you guys more about the results after I talk to you guys about the experiment. So let me go ahead and do the synthesis part. So the synthesis part, let me share the PowerPoint with you in this, and you will see this PowerPoint again in the video so that you guys have an idea of what exactly is going on in this experiment. So this is the preparation and analysis of the nickel salt. First thing that you guys should know is that the nickel salt is what we call coordinated complex. Remember when we talked about Lewis acids and Lewis base, and that the metal ion is going to surround itself with water? Well, this is what we have. We have nickel. The salt is nickel sulfate. This is the positive, nickel plus 2, sulfate's negative 2. That's why it's a salt, because you have a cation and an anion. But nickel actually is attracting water through the hydration. It's actually coordinated. When a metal complex binds, the water's called ligands. Okay, they're called ligands. Ligands are the chemical parts that binds to the metal. So H2O, even though I write it as OH2, H2O, I'm just showing you that the point of attraction through the oxygen lone pair. Okay, so there are 6 waters here, 1 sulfate, and then this chemical right here is called ethylene. Ethyl means 2 carbons. There's 2 carbons right here. Ethylene diamine. Amine means ammonia. So if you take a look at this nitrogen right here, you can see that if we replace this carbon with a hydrogen, that would be ammonia, NH3. Whenever you have ammonia-like structure in chemistry, especially organic chemistry, we don't call it ammonia anymore. We call it amine. That's the name of the ligand when it binds to the metal. So we're replacing this 2 of these water with this ethylene diamine. Okay, so the structure itself will be the ethylene diamine replacing 2 of the water. You can have 1 ethylene diamine, 2 ethylene diamine, or 3 ethylene diamine. And that's what you see in this PowerPoint right here. Okay. The objective, of course, is to synthesize a nickel ethylene diamine from nickel sulfate hexahydrate, and then to analyze what the formula, the true formula is for the nickel ethylene diamine complex. Okay, that's what the goal of this experiment. You should write a little bit more details other than that. I just kind of told you the overarching objective. There's more to it than that, of course, but that's the main objective of this experiment. Now, when we write ethylenediamine, this is the chemical. And the reason why we draw it in this fashion with the lone pair showing is because that's where the nitrogen binds with the metal, okay? And when we have the nickel sulfate hexahydrate, remember the nickel sulfate hexahydrate is this chemical right here? Well, that chemical right there is green, as you can see right here. And we write it NiSO4 because that's the salt. And then the 6 water sort of hydrating to the nickel. Okay, the formula and the shape is not exactly the same, but that's basically it. So in the first step and in the synthesis, you guys are actually doing 3 separate syntheses. Okay, but in one of those syntheses, what you are doing is you're taking this salt, nickel sulfate hexahydrate, you're adding ethylenediamine. And remember, when you do a synthesis, you can't add ethylenediamine one time. You add a bunch at a time and hope for just one substitution like that. Okay, and when one of the ethylenediamine kicks out 2 of the water, then that's the salt that you get. And it looks sort of bluish. We call that salt A. Now, another synthesis will require us to take this nickel sulfate hexahydrate and add a little bit more of nickel ethylenediamine. So this arrow really is not this. This arrow is from here to here. And we get this salt, where 2 more water is removed and 1 ethylenediamine is replaced. Now, in chemistry, what we do is, well, chemists are pretty lazy, okay? And so instead of writing the carbons and the hydrogens throughout, what we do is we do a shortcut where we just show the carbon, the nitrogens of interest right here. And then these bends right here represents carbon. This bend right here represent carbon, and carbon always has 4 bonds. That's a cardinal rule that you have to remember in organic chemistry. Because this carbon right here, oops, this carbon right here already has 2, that means that the other 2 is bonded to hydrogen. Okay, it's bonded to hydrogen. So you can have this type of structure when you replace 4 of the waters, or you can have this. Notice how these 2 waters are adjacent to each other. They're 90 degrees apart, whereas in this configuration, they're 180 degrees apart. These are what we call isomers. Okay, these are isomers. The chemical that you guys are actually going to be synthesizing is this, because this is more stable. Okay, it's much more stable. But they both have the same formula. Isomers are chemicals with the same formula, different structure. Okay, so that's with 2 ethylenediamine replacing 4 waters. Replacing 4 waters. And then the third salt, so you would actually draw an arrow in one of the synthetic scheme from here to here, is where all 6 waters are replaced by 3 ethylenediamine. Now notice it takes 3 ethylenediamine to replace 6 waters. Why? Because the ethylenediamine takes up 2 bonds on the nickel per ethylenediamine. Notice the different colors of these things. And that's important because the colors will give you a clue as to which salt you have. Okay, so that's the general scheme here. And these are the possible salts. Okay, and so this is the general formula up here. Okay, this is the general formula up here. It tells you that you have ethylenediamine. We don't write ethylenediamine as a whole word. We abbreviate it as EN. EN represents this guy right here. This guy right here, EN. Again, because we're lazy. You just have to sort of remember that. Here's how this general formula works in terms of this structure. When EN is 0, see X here is 0, that means there is no ethylenediamine. 6 minus 0 is 6 waters. You have a sulfate, and then there's other waters that are going to be outside the coordination sphere. The coordination sphere means that whatever is bonded to nickel is called the coordination sphere, because those are the chemicals that are attached directly to the nickel. Okay, anything outside of that, like if I have a water out here somewhere, that would be outside the coordination sphere. Water will always be there because your products could be wet. And so we put Y as a variable, H2O. But if X is 0, you've got 6 waters, 1 sulfate, and various amount of water outside the coordination sphere. If X is 1, that means you have 1 ethylene-diamine replacing 2 of the waters. So 6 minus 2 is 4 H2O. And then, of course, you still have water outside the coordination sphere. Okay. If X is 2, then you have 2 ethylene-diamine replacing 4 of the water. And 6 minus 4 is 2. So there's 2 waters bound to the nickel. And then you have extra waters, if you have that, outside the coordination sphere. And then if X equals 3, then you have all 6 waters that were originally bonded to nickel replaced by the 3 ethylene-diamine, represented by En, or these NN with this bridge type structure. That's ethylene-diamine. And the formula here will be nickel En3. Remember, 6 minus 6 is 0. So it's just nickel En3 sulfate and then whatever water. What the wild card in this analysis is water. There's going to be a certain amount of water, 6 maximum, that's bonded to the nickel. But you may calculate a higher formula weight than a chemical. You assign the extra AMU to water. And that'll become more obvious when you look at the calculation. But you have water that is within the coordination sphere, and you may or may not have water outside the coordination sphere. Okay, that's one thing I want you guys to remember. So the synthesis of salt A, you take, and pay attention to this, you take a certain mass of nickel sulfate. Here is what I was talking about. Let me go back to that. Thanks. You know what I'm going to do from this point on? I'm just going to say next slide, and hopefully you guys can remind me that you are getting the next slide, because even though I have my second screen here, I'm always pointing at looking at what I have. So here's what I mean by what I was talking about previously. See how you have ethylene-diamine, En here? Well, that represents the ethylene-diamine that I'm talking about in these salts. Okay, it's a salt because you got a cation and anion. So when X equals 0, you have this original starting material. When X equals 1, you've got 1 ethylene-diamine replacing 2 of the water. When X equals 2, you got 2 ethylene-diamines replacing 4 of the water. 6 minus 4 is 2 remaining waters. When X equals 3, all the waters are removed, and you've got 3 ethylene-diamines. There's always going to be a water outside this coordination sphere. Anything in the bracket here means that those are the chemicals directly bonded to the nickel. But outside that bracket, they could be water that's just adhering to the chemical. It's stuck in there, in the crystal somewhere. So we need to account for that in your experiment by indicating there's Y amount of water, and Y is going to be a number like 3 or 4 or 2 or even 0 if it's completely dry. Okay, so this is the scheme I want you guys to remember in terms of why we use this generic formula. But then if we want to talk about a specific salt, like salt A would be X equals 1, it would be this guy. Salt C would be X equals 3, it would be this guy. So I'm going to the next slide. And this is the synthesis of salt A. We take water, about 5 milliliters of that. We weigh out the nickel sulfate hexahydrate, and it's about 1.25 XX grams. You see the exact mass in the data sheet. Okay, and and then we add it to water, and then we add about 25% ethylenediamine. It's actually ethylenediamine solution. It's 25% of 1 milliliter. So if you think about it, it's 20.25 milliliters of ethylenediamine. But we're adding 1 milliliter of 25% ethylenediamine. And then what we do is we continue to stir, and what will happen is that we put it in an ice bath and crystal starts to form. Okay, we wait, and then when the crystal forms, we do a vacuum filtration where we hook up our Erlenmeyer flask with a sidearm to the vacuum. We have a glass frit. It's like a funnel with a filter, except the filter paper is sort of a porous solid. And then we can filter out the crystals that we have and let the liquid with all the other contaminants or the excess residue filter through. And this is what it looks like from a headshot right here. And again, what we're going to do is we're going to dry it because we don't want much water there. We only want the water that's sticking to the nickel. So we do this by washing it with ethanol. The reason why we use ethanol is because ethanol doesn't dissolve the solid. If we put water in here, it actually dissolves your precipitate, and then your yield is how much you recover at the end, would be lower. So we're washing it with cold ethanol, and then overnight, okay, this would be like 1 day overnight or a couple of days in the next lab period, it would be dry, and then we weigh it and store it. Okay, so that's the synthesis of nickel salt. Pay close attention to the only difference between the three techniques is the amount of nickel sulfate we have and the amount of ethylenediamines that we are adding. Okay, so let's take a look at salt B. That's what salt A looks like. And we recover 1.2582 grams. That's the amount that's recovered. And that's also in your Excel data sheet. So I'm going to the next slide. This is the synthesis of salt B. And in this slide, again, we measure out 5 milliliters of water. And we weigh out, actually, this is the mass that we weighed out, 1.2752. The direction calls for weighing about 1.25, but when you actually go to the scale and weigh these things out, it's going to be in that ballpark, okay? So it's 1.2752 grams of that starting material. Then we're putting it in water, we're dissolving it, and then we're pouring 2.5 milliliters of 25% ethylenediamine. Remember salt A, we only poured 1 milliliter. Well, this one we're pouring 2.5, so there's more ethylenediamine. Okay, and then we are stirring it, continuously stirring. Okay, until we have a color change, and then when we recover it, we stick it in the ice bath again. Wait some time for the crystals to form. And this is what it looks like from the top view. You can see it's sort of lavender-like type. We do a vacuum filtration again. So we wash it with, there should be ethanol here. I forgot to show the ethanol, but we're washing it with ethanol so that there's no excess water. And then after it dries overnight, we weigh it. And then this is what it looks like when it's dry. Okay, that's the color that you have. So this color that you see in the scale is sort of misleading. This is actually what it looks like when it's wet. This is what it looks like when it's dry. Okay, so that's salt B. Let's take a look at salt C. Salt C, again, you do the same procedure. You have 5 milliliters of water. You weigh about 1 gram less nickel now. In fact, the mass is 1.0703 grams right here. And then we transfer it into the 5 milliliters of water. And then we add 3.5 milliliters of 25% ethylenediamine. So for salt A, we added 1 milliliter. Salt B, we added 2.5. Salt C, we added 3.5 milliliters of ethylenediamine. We wash it with ethanol. Okay, this is what it looks like. Well, we cool it down. We wash it with ethanol, and then we filter it through, and this is the color of that particular salt. Pay attention to the different colors of this salt because it tells you they are different compounds. The color is a good way to indicate you have different compounds or at least some contaminants. The mass of the final products, 1.2631 grams, and this is what it looks like in the end. Okay, this is the data of salt A, B, and C. We started with 1.2801 starting material, 1.2752 of starting material for salt B, and 1.0703 grams of starting material for salt C. The final products are 1.2582, 1.3937, and 1.2631. Those are the before and after. And these are what it looks like. Okay? These are what it looks like when they're wet and when they're dry. Now, one of the things that you should do, or you would have done when you isolated the salts, is you needed to put some of them in water and take an absorption spectrum. Remember, an absorption spectrum is what we did in experiment 1 and experiment 2. It basically tells you what absorbance these things have depending on the color of that particular chemical. So this one right down here, this is the one that's blue. That's when X equals 0. So your starting material is this one way down here. That's the absorption spectrum. The maximum, the absorbent maximum is about 400 nanometers. That's this right here. When X equals 1, you have this violet type of color right here. Okay, and notice that the maximum wavelength by which it absorbs is lower in wavelength, higher in energy. It's down here. That's probably about 390 or somewhere thereabouts. When X equals 2, you have this compound right here. This is the absorbance. And you notice again that it's going to be shifting to shorter wavelength, higher energy. Higher energy is to the left. Shorter wavelength is higher energy. And then when X equals 3, oops, sorry about that. When X equals 3, then we have this. It has the shortest wavelength. Okay, so that's your synthesis part. That's your synthesis part. Now let me talk to you guys about your analysis part. Okay, I'm now outside. Let me, so this is the slide that says nickel salt synthesis. I'm going to close that. And now I'm going to do the nickel salt analysis. I believe that's what, let me close this real quick. Sorry about that. Open this up. And let me share that with you. So once you've synthesized the 3 salts and you cleaned it up and you put it in your filter paper and then you dry it overnight and then you weighed it. That was the first thing that you would have done, is weighed it. Then the next period is the analysis, and the analysis actually takes 2 days because you're analyzing for the nickel, and then you're also analyzing for the ethylenediamine. Okay, so this is the procedure for the analysis part, and then I'll show you the video. Let me share that screen with you because I can see that that particular is not being shared right now. So I need to share that. Hold on. I think we are here. Share. So you guys should see at this point preparation and analysis of a nickel salt. And this, I believe, is the analysis portion. Yeah, this is the analysis portion. Okay. So again, this is just the opening slide. Let me change this to a PowerPoint. Can you see that? Resume sharing. Okay, let me redo this because right now you guys aren't seeing that. Okay. So again, in this second part, you guys are going to be analyzing the salts that you synthesized from part 1. And in this particular part, you're actually going to determine how many ethylenediamines you have in each of your salt. The ethylenediamine is going to be analyzed by titration, back titration. The nickel and the sulfate will be analyzed doing a spectroscopy method by figuring out what the concentration of the nickel is. So these are the two methods. So again, I remind you about the synthesis and the different salts, A, B, and C. I remind you about the different formulas, X equals 1, X equals 2, X equals 3. All right. Then I remind you of the data. The first part of this is actually ethylenediamine. Okay. Ethylenediamine is this guy right here. It's got one hydrogen, one hydrogen. It's connected to a carbon. The carbon has one hydrogen, two hydrogen, connected to another carbon, a hydrogen, connected to a nitrogen, lone pairs, a hydrogen, and a hydrogen. The formula for this guy is C2H, let's count, 1, 2, 3, 4, 5, 6, 7, 8, and 2. That's the formula of ethylenediamine. Because we are lazy folks, we write it this way. Because we are even lazier folks, we write it this way. And because we are super lazy, we write it this way. Okay, they all mean the same thing, except we're just using different nomenclatures to kind of like streamline the process. So this right here is represented by that formula. In fact, all of these are represented by that formula. In organic chemistry, when you get to organic chemistry, carbon always has 4 bonds. So when you see 2, you know that the other 2 that you don't see is 2 hydrogen. In a structure like this, where there's carbon has 1, 2, 3 bonds, then you would only put 1 other hydrogen. Okay, but that's something that you guys will learn when you get into organic chemistry. Okay, so that's ethylenediamine. Now, what I want to show you is that ethylenediamine is a base, just like ammonia is a base. Okay, just like ammonia is a base. So I'm going to erase this right here. I'm going to show you the chemistry of this guy. And you need to appreciate the chemistry because that's exactly what you guys are going to be doing in this first analysis, is you guys are going to be titrating it. So this is what you guys are going to be doing in this part. You got ethylenediamine, and then you're going to add HCl to this. Okay, you're going to add an excess of HCl. And what HCl will do is it will donate its hydrogen to this and this. What happens is that you have the nickel and you've got the ethylenediamine right here, like that. Okay, depending on which salt you have. When you add HCl, you're going to cleave this. You're going to break that bond. And so the nickel will be floating around. The solution will turn green because it doesn't have the ethylenediamine complex anymore. And the ethylenediamine will be free to float around in the solution. So the first thing that you will do to your salt, each of your salt, is you're going to put in, I believe, sulfuric acid. And the acid cleaves that nitrogen to nickel bond. And it makes these things float around. And so the nickel will be free, but you're not analyzing for the nickel. You're analyzing for how many ethylenediamines were originally in your compound. Now that it's free, you add hydrochloric acid, and the hydrochloric acid will bond to the nickel. For every 1 ethylenediamine, you need 2 hydrochloric acid. Okay. The key is that, let's say we have 30 ethylenediamine, just for the sake of throwing out numbers. Okay. What you guys are going to be doing is not add 30 because you don't know how many ethylenediamine you have. Okay. That's what you have to analyze for. But you're going to be throwing an excess amount of hydrochloric acid. Let's say that I throw in 75 hydrochloric acid, an excess amount, an abundance amount. Well, you know that if you had 30 originally, okay, you won't know that. But if you did have 30, then 60 of that would be used to bind the ethylenediamine. Remember that it takes 2 hydrochloric acid for every 1 ethylenediamine. So the fact that you had 130 ethylenediamine means you need 60 HCl. Okay, I hope I'm not losing you, because this is the basis of your analysis. That's why it's called a back titration. Okay, that means that there are 15 HCl still roaming around in that solution. Let me try and illustrate that with a diagram here. Okay, let me try and illustrate that with a diagram here, because it really is important to understand the chemistry. I always want to stress the chemistry, because when you can see the chemistry, then you see how the analysis is done. Okay, so let's take a look at this. You have a beaker, okay, and you put in here your salt. It could be A, B, or C, but it's going to be NiEnX H2O 6x minus 6 minus 2x sulfate Y water. It's basically whatever salt you have in there. Okay, that's your salt in here. You're going to be adding an excess amount of hydrochloric acid, and depending on how many ethylenediamine you have in there, that is free, because you've caused the nickel to unlatch its ethylenediamine. Now the ethylenediamine is free. Depending on how many ethylenediamine, it's going to tie up to hydrochloric acid. In our example here, we have 30 ethylenediamine. We add 75 waters. That means there are 15 moles or 15 HCl's in there. Okay, that's the acid, strong acid left over in excess. Now here's why it's called a back titration. You take that solution now. You take that solution, okay? And what you do to that solution is you titrate it with sodium hydroxide. Okay, you titrate it with sodium hydroxide. And you notice when you reach the endpoint, because you put an indicator in there, and when you reach the endpoint, whatever, you know the concentration of sodium hydroxide, you'll be given that concentration. And what you will do is you add the sodium hydroxide until you reach the endpoint. The endpoint's where the indicator changed color. Knowing the concentration of sodium hydroxide and knowing the volume, you now have the moles of the base, which, guess what, is equal to the moles of HCl or H plus unreacted. So do you understand that? You're adding HCl, it's in excess. Some of it goes unreacted. What you are doing is you're titrating that excess that went unreacted to the equivalence point. Now, when you reach the equivalent point, you know how many. The key here is that, let me try and talk to you until my other computers boots up. You guys are titrating the excess unreacted hydrochloric acid. So when you reach the endpoint, the moles of the hydroxide is equal to the excess hydrochloric acid that went unreacted. So you know how much hydrochloric acid you added initially. Okay, you know how much hydrochloric acid you added initially. If you subtract off the amount that went unreacted, you now know the moles of hydrochloric acid that reacted with the ethylenediamine. If you take that moles of hydrochloric acid and divide it by 2, that is the moles of the nickel in your compound, the moles of the ethylenediamine in your compound. So that's how you do the ethylenediamine analysis. It's called a back titration because you're putting an excess amount of hydrochloric acid. Some of it will bind to the ethylenediamine. The excess does not. You titrate that excess with sodium hydroxide. So you take the moles of HCl you originally added, subtract the moles that was reacted with sodium hydroxide. That difference is the amount of hydrochloric acid that reacted with the ethylene diamine. Divide that by 2. Now you have the moles of ethylene diamine. That's what you need in your analysis. Now, the second part of this titration is the analysis of your nickel. And remember, in the formula, for every 1 mole of nickel, you also have the same mole of sulfate. They're 1-to-1 because nickel's +2, sulfate's -2. So they have to be in equal amounts. They have to be in equal amounts. So when you analyze for, if you know the moles of the nickel, you also know the moles of the sulfate. That's key. If you know the moles of the nickel, you also have know the moles of the sulfate. So how do we determine the moles of the nickel? Well, you do that by spectroscopy. Okay, you do that by spectroscopy. And in spectroscopy, what you will do is you will take certain concentrations of nickel and create a standardization curve, just like in activity number 4. Remember in activity number 4, you guys did cobalt chloride and you had different concentrations. And then you took your unknown, measure that absorbance, and then you can figure out the concentration. Well, that's exactly what you are doing in the second analysis here. What you guys are doing is you're making a standardization curve of nickel. And the reason why you can do that with your salt is because when you put acid in your salt, the ethylene diamine and the nickel breaks apart. And the nickel is going to be sitting there. Yeah, there's ethylene diamine as well, but ethylene diamine doesn't absorb any color. It's the nickel that is green. That's why your original starting material is green crystals. But what you guys are going to be doing is calculating the concentration of that nickel based on spectroscopy. So let me go back. This is the PowerPoint for the titration. You weigh a certain amount of salt. You add hydrochloric acid. It's 10 milliliters of 0.1994. That's an excess amount, okay? The concentration is 0.1994 molars of hydrochloric acid. So these are the possible salts right here, okay? And then you put it into, you add hydrochloric acid. Notice the color changes automatically. It now looks transparent. And what you guys are going to do is put methyl red indicator, not phenolphthalein, but methyl red, and then you're going to titrate it to the endpoint. So if you know the volume of sodium hydroxide, the sodium hydroxide is 0.09697 molar. If you know the volume of hydroxide and the concentration of hydroxide, then you can calculate the moles of the hydroxide. From here, you know that you have the concentration of hydrochloric acid and the volume of hydrochloric acid. So you can calculate the excess or the amount of hydrochloric acid that you react. So if you take this moles of hydrochloric acid and you subtract the moles of hydroxide, which is really equal to the moles of HCl that went unreacted, you now know the moles of HCl that reacted with the ethylene diamine. If you take that moles and divide it by 2, you have the ethylene diamine moles in your salt, okay? That's what the procedure calls for. So in this part right here, this is the second part. This is the nickel analysis. So what happens is that you weigh a certain amount of your salt, again, all 3 salts. You weigh it, and then I take that back. I'll hold off on that statement. You take the original starting material, the nickel sulfate hexahydrate. You weigh a certain amount, you make a stock solution. And then from the stock solution, you do a serial dilution. So you make 3 solutions from that stock solution that are lower in concentration. And this is what it looks like, okay? If you were in lab, you would make a total of 3. Since I did this experiment, I made a total of 5, okay? Don't worry, you guys don't have to do the procedure. You just need to be able to analyze the results. So these are the data points for the 5 solution, it should be a linear graph. Okay, that's just for the nickel. This calibration curve right here is for the nickel +2. What you will do next is you will take one of your salts. Okay, you take one of your salts, put it and prepare a solution, and then measure the absorbance. Measure the absorbance, and the absorbance should fall between these points. What you can do now is you can read the absorbance and back calculate the concentration of your nickel using that calibration curve, or using the equation of the line. Okay, using the equation of the line, you can back calculate the moles or the molarity of the nickel using the calibration curve. So this is the calibration curve that you guys are generating from these standards. It comes from the original salt. This is what it looks like. Then you take your unknowns, prepare a solution. I think it's 25 milliliters. So you got to remember that as a dilution factor. Okay. You want to go in here and measure the absorbance. Whatever that absorbance is, you can use this curve to figure out what the concentration of your nickel +2 is in your unknown. You do a bunch of dilution correction, and then you can calculate the moles of the nickel. That's how you would do the analysis for the nickel. Okay, so this is what it looks like. And then, again, that's the absorbance. This is the data for that calibration curve. This is the data for the calibration curve. Notice that standard 1 has 0.0152 molarity. It's got a standard deviation 0.001. When you're measuring these things, it gives you the concentration directly based on the absorbance that it measures. These are the absorbance that it measures, and it averages a concentration. Standard 2 is 0.03044. Standard 3, 0.054566. Standard 4 is 0.6087. Standard 5, 0.07. So this is the equation, or this is the line that's generated from this calibration curve. So see this curve right here? This curve right here, well, this is the full analysis. That's that, okay? You can see that the correlation factor is 0.99943, so it's pretty good, okay? The equation of the line is Y, which is absorbance, mx, m, the slope is 5.16950, x is the concentration plus the intercept, 0.06773. You're going to use this equation to calculate the concentration of your nickel for your unknown. So that's the experiment. Now let me go back to Canvas. This right here is the PowerPoint. This right here is part 1. This is the YouTube for the synthesis portion. I'm just going to scrub through this so you guys can see what is in this video. So I'm just going to scrub through this real quick. That's basically a discussion of the PowerPoint. Okay, let's go back. This right here is part 2. And I'm going to scrub through this again. And in this case, I'm actually doing the experiment for you. Okay, notice the concentrations 0.1994 for the hydrochloric acid. I'm adding 10 milliliters of that. I'm going to fast forward this, and then I'm titrating. Addition of methyl red indicator, and then I'm titrating this with sodium hydroxide to the endpoint, and this is what the endpoint will look like. And then I record the final volume of sodium hydroxide, endpoint to pink to yellow. That's what the endpoint looks like. And then I record. This is the titration curve. This is the titration curve. Now, the question I have for you guys, maybe you can include this in your discussion. Maybe you get bonus points. Is why is there two inflection? Okay, why is there two inflection here? So think about that. Think about the system. This is the data. So this is for salt A. This is the amount that I weighed out for that analysis. This is the volume of hydrochloric acid I added. You know the concentration of hydrochloric acid is, let me go back. Let me stop this. 0.1994. This is the amount of sodium hydroxide that I added to reach the endpoint. I need to stop this real quick. Let me pause this. Okay, so those are the different titration curve for the different salts. And then you guys could probably control the here. I want to talk to you guys about this. Let me pause that. Okay, so this is salt A. This is the mass that I weighed out for the analysis. Volume of hydrochloric acid at 0.1994 grams. It's still going. I thought I paused it. Okay. Okay. This is the volume of sodium hydroxide. The concentration is 0.09697. Now you notice I don't give you the first volume, the first trial, and that's because you have to write that from the movie. You actually have to watch the movie and record that so that now you have the volume from the movie right here. Okay, I give you the other two. Same thing with the analysis of salt B. I don't give you the first one. You have to find that in the movie. I give you the other two, and then also from the three. So this is your ethylenediamine analysis. Okay, so that is the that part. For the nickel analysis, this is what it looks like. Okay, I'm showing you the PowerPoint in which that happens. And then I'm actually recording the absorbance for, see how they're all green for your unknown? That's because it's the nickel that's being analyzed. And this right here is the data set that you would have to generate that calibration curve and then record from your Excel spreadsheet that you will download the absorbance and then the concentration of the nickel. You guys have to do that. Okay, and that's basically the movie for the two procedures. Let's take a look at the data sheet. So I'm going to open up the data sheet. Now I want to talk to you guys a little bit about this and then we're done. Again, this is the initial mass of the starting material. This is the final mass of the product for salt A, salt B, salt C. This right here is the titration curve analysis for ethylenediamine. Salt A, I do 3 trials. This is the mass per trial. I'm using 10 milliliters for each one of these, but then I come to a different endpoint for the 3 methods because I have different mass. So of course I'm going to have different endpoints. I have different amount of ethylenediamine. This is salt B, and notice that my the amount of sodium hydroxide is lower than in salt A. Think about that a moment and think why it should be lowered. For salt C, again, this is the mass that I started with. And again, it's much lower than either B or C. So this is your ethylenediamine analysis. That's the data that you would use. These are what the titration curve look like when you do the titration. Okay, that's salt. That right there is first trial, trial 1, salt A. Remember I told you that you guys need to find that volume at the equivalence point and put it in here. Well, I give you the titration curve. You guys should be able to find that in this titration curve. This is salt B, and I give you that titration curve. and then this is salt C. And again, I give you that titration curve. The dots are the actual data. The line is my best guess in approximation using a line in Excel so that it connects the dot. Anyway, if you're looking for the equivalence point, what you want to do is look at the equivalence point on the original data, because if these mass are sort of similar, then these volumes are going to be very, very similar. Just a hint. Okay, let's take a look at the nickel analysis. So this is your concentration. These are the absorbance. This is for the calibration curve. Concentration, absorbance. And what you want to do is plot this in Excel. Plot this concentration versus absorbance, so you have an equation of the line. I think I already showed you that in the movie. But then you want to do a Linus, because you want to know the slope and the intercept. Okay? Because once you know the slope and the intercept, the absorbance here is going to be plugged in for the equation. And what you guys are going to be doing is calculating the intercept, which will give you the concentration of that. So you're working backwards. If you're given the absorbance now for your different salts, you should be able to back calculate the concentration using Beer's law equation. Okay, so think about that. And you do that for all three. Okay. I actually give you that equation here, but I want you guys to reproduce that through Linus so that you guys will have that exercise. So with that data, you guys can now calculate the amount, the moles of the ethylenediamine and the moles of your nickel, and figure out what the chemical formula is. Okay, you guys can calculate that. Let me finish up with some basic chemistry 200 that you guys already know how to do. Okay, let me just give you an outline of the calculation that you guys are going to be doing when you do this. So here's what you guys are going to be doing in your analysis. You're going to have say nickel, ENX, H2O, 6 minus 2X, SO4, Y, H2O. Okay, so from the titration, you guys are going to be able to calculate the moles of ethylenediamine, the moles of C2H8N2. You guys are going to be able to calculate that. Now, what is important, and you guys remember from general chemistry, that if you have the moles of ethylenediamine, then you can get the mass of ethylenediamine. How do you do that? You just use the molar mass, and the molar mass of ethylenediamine is about 60.0 grams per mole. Why do you need the mass? Because you need to know what is the percent ethylenediamine in this salt that you have. And why is that important? Because you guys are doing chemical analysis, okay? Elemental analysis. So if you have the mass, then you take the mass of the ethylenediamine that you calculated here, and you divide it by the mass of the salt. That's the mass that you weighed out for this analysis. And you multiply that by 100. Now you have your percent ethylenediamine. And for all three trials, that percent should be very close. Okay, that's important. Remember that, remember that. Now what you guys are going to be doing in the nickel analysis is you guys are going to be getting the concentration of your nickel. Remember that the calibration curve only gives you the concentration of your nickel. So if you take the concentration of your nickel, which is moles per liter, and you multiply it by the dilution factor, the volume that you have, let's say we convert this to liter, then you have your moles of your nickel. Okay, that moles of your nickel is also the moles of your sulfate, by the way. Why? Because in the formula, for every 1 mole of nickel, you also have 1 mole sulfate. Those are the only two chemicals that are charged, and they have to be equal to each other. Otherwise, the chemical won't be neutral. So let's go back here. Okay, now that you have your moles of your nickel, you can convert that to mass of nickel using the atomic weight. Okay, so you need your moles of your nickel first to get the mass of the nickel. Why do you need your mass of the nickel? Because you can take the mass of your nickel and divide by the original mass that you analyze. This is the original mass that you analyze. Multiply that by 100, and now you get your percent of your nickel. Okay, so from the calibration curve in your absorption analysis, from the concentration, you're going to get the moles. From the moles, you're going to get the mass. And from the mass, you can get your percent nickel. You do that also for your moles of sulfate. From your moles of sulfate, you can get the mass of the sulfate. Remember, these two are equal, but their mass is not equal because they have different molar mass. Sulfate is about 96.0 grams per mole. Make sure you use a more accurate value. Now, if you take the mass of your sulfate and divide by the mass of your sample, and these two are the same because it's the same sample for that analysis, then you get the percent of your sulfate. So remember that your salt is going to contain nickel, sulfate, ethylenediamine, and water. You never did do an analysis for water, but that's okay because your percent nickel, your percent sulfate, and your percent ethylenediamine and percent water should add up to 100%. It has to add up to 100. So you will have this, this, and this. This guy, therefore, is determined by 100 minus percent nickel minus percent sulfate minus percent ethylenediamine, and that's your water, your percent water. You do it by difference. That means the water has the biggest error, because if you have any error in any of these, it leads to the error in water. Okay, now that you have your percent nickel, percent sulfate, percent ethylenediamine, and percent water, assume you have 100 grams. Take your 100 grams and get the moles of the nickel, the moles of your sulfate, and it's not the same as these up here because now you're doing it based on 100 grams of sample, moles of ethylenediamine, and moles of water. Why is that important? Because now that gives you the chemical formula. Nickel, moles, sulfate, moles, ethylenediamine, moles, and then water, moles. That's your chemical formula. Now remember that your moles here may not be whole numbers. It might be 0.086. Well, you need to remember that the formula is always based on whole numbers. So if you have something like 0.086 here, and this also should be 0.086, and this is like 0.163, and this is like 0.240, then you look for the smallest number and you divide by the lowest number, 0.086, 0.086, 0.086, 0.086. This now becomes 1, This now becomes 1. This, I believe, is 2, and whatever this number is. I think it's like 8 times, it's like 3 or 4. Okay, so that would be your formula for that analysis. So it's going back to general chemistry. It's going back to general chemistry and applying what you guys already learned from general chemistry in this analysis. I apologize for that chicken scratch there, but you get the idea. The only thing, the only Chem 201 about this whole lab is that you're working with coordination compounds. The rest is general chemistry. You guys know how to do that. So that's all I have for today. I think we've covered both the synthesis and the analysis part. Look at the Zoom video if you are still confused about that, because you really got to get the correct formula and you need to show your work in the write-up. Okay? You need to show your work in the write-up in order to do this. And then I'll be around, of course, all week. We're not meeting on Wednesday again, but I'll be around all week. If you have any specific questions, remember, you don't have to do the analysis for the data and observation. You just have to record what you're observing and record the data, fill in the blank, in other words. What was the equivalent volume for that first trial? And that's it. Give me your pre-lab, give me your data and observations, and then that's what's due Sunday. And then if we need to, we can talk about more of the analysis next Monday. Okay, but yeah, I told you this is a very long lab, but it's actually a good lab because it reviews a lot of the chemistry that you guys need to remember.